I want to talk tonight about factors that affect nucleophilic substitution reactions. Start by looking at the alkyl halide. We're going to compare SN1 to SN2 reactions. Now recall that SN2 reaction resembles this sort of process where a nucleophile comes in and a leaving group leaves in one single step, and it's a second order reaction. In an SN1 reaction, the reaction occurs in two steps. The leaving group leaves, and then the nucleophile comes in and attacks the formed carbocation. In this particular case, at the end of the reaction, my hydrogen leaves to give me my neutral sulfide. This is a first order reaction because the rate determining step is this very first step where the leaving group leaves. First, to remember a couple of things. First, primary alkyl halides will always proceed through an SN2 mechanism. There are a few exceptions to this, but we're going to focus on the fact that most of them, the large majority, proceed through an SN2 mechanism. On the other hand, tertiary alkyl halides will always proceed through an SN1 mechanism. For secondary alkyl halides, the course the reaction takes, SN1 or SN2, depends on the conditions of the reaction. Big question we have to ask and answer is why? Start off looking at the SN2 reaction, and I want to start off looking at the SN2 reaction on a primary alkyl halide like this one and like this reaction. And what we're going to look at first is not going directly from the reactant to the product, but we're going to look at what the transition state for this reaction looks like. This is the transition state, and when we draw a transition state, we always put it in brackets, and we use this little symbol here to indicate it's a transition state. And what you can see is in our transition state, the bond to my leaving group, my iodine, is starting to break. The bond to my nucleophile, my bromine, is starting to form. I have a partial negative on the iodine. As it starts to gain negative charge, I have a partial negative on the bromine, which was a full negative as it starts to form a bond and lose its negative charge. And I've got these other three groups sort of in a plane in the middle. And that's what my transition state looks like. And as I proceed to the product, the bond to the bromine forms, the bond to my iodine breaks, my alkyl bromide. So that's what it looks like for a primary alkyl halide. I want to look at the same reaction except for a tertiary alkyl halide. Again, I have an alkyl iodide. This time it's tertiary. I have my nucleophile, and if I look at the transition state, it looks something like with this, the same features as for the primary alkyl halide, with the bromine coming in, the iodide leaving, and the other three groups around the central carbon for a total of 5 groups around the carbon. And then the final product looks like this with my bromine replacing my iodine. Now, as we said, the first reaction will happen readily. The second reaction won't happen readily. And I want to talk about why that is. And what I want to focus on first is what's going on around the central carbon where the reaction is happening. What you notice in particular is that around this central carbon, there are 1, 2, 3, 4, 5 groups in both cases. And this is more than carbon normally typically likes to accommodate. Normally we say the most things around a central carbon atom are 4 things. Well, 5 is more than 4 obviously, and it makes this carbon particularly crowded. Anything that increases this crowding makes the situation worse and slows down the reaction. Well, in the case of the primary alkyl halide, this carbon has 2 hydrogens on it. These 2 hydrogens are smaller than the 2 methyl groups. That means that this, in the primary case, is less crowded than in the tertiary case. On the other hand, the crowding is significant enough for the tertiary alkyl halide that it actually makes this reaction so slow that it's impractical. Or because of this crowding, we don't get a SN2 reaction on the tertiary alkyl halide. Prepared a couple of models showing this. This is the case of the primary alkyl halide with the bond for the nucleophile forming and the leaving group breaking, and you can see the other 3 groups around it. Same thing for the tertiary alkyl halide, and you can see with those methyl groups there compared to my colored hydrogens here, there's much more crowding, which is consistent with what we were saying. We want to look at an SN1 reaction and try to answer the question, why does a tertiary alkyl halide proceed much more rapidly by the SN1 mechanism than a primary alkyl halide? Looking at a primary alkyl chloride first, and the first thing that happens in the SN1 mechanism is my leaving group leaves, gives me my carbocation. Notice that this is an equilibrium reaction, and the reaction goes back and forth. I should also include the Cl- that's released here as well. In my second step, my nucleophile comes in and reacts with this carbocation in my product. I can draw a similar mechanism for the SN1 reaction for a tertiary alkyl chloride. Group leaves. First step, giving me my carbocation, which is then attacked by my nucleophile. The important thing for us to remember is that the first step, this equilibrium step, is our rate determining step. Because of this, we only need to look at the first step in order to determine which of these two reactions is faster. And that's what we're going to do. We're going to look at this first step. We're going to ignore the second step. What I'm going to do is make an energy diagram for the first step of the primary SN1 reaction versus the primary SN2 reaction, where we look at the reactants and the products, and we have increasing energy on this axis. And if we look at the SN1 process on a primary alkyl halide first, it looks something like this. We're breaking the carbon-chlorine bond, so it's going to be endothermic, and the reactant's down here, and the resultant carbocation is up here. If we compare the same trace to the trace for the this trace to the trace for the tertiary alkyl halide, in the case of the tertiary alkyl halide, the trace looks like this. And I want you to notice two things. The first thing is that the energy barrier for forming the tertiary alkyl, the tertiary carbocation, is lower than for forming the primary carbocation. This means that the tertiary carbocation is formed faster. Notice that the tertiary carbocation is lower in energy than the primary carbocation. The tertiary carbocation is lower in energy. That means, notice this is an equilibrium reaction, that at equilibrium we have more of the tertiary carbocation than we do of the primary carbocation. This means that for the tertiary alkyl halide, the SN1 reaction goes much faster than the case of the primary alkyl halide. In fact, the primary alkyl halide goes so slow that we don't even usually consider SN1 for a primary alkyl halide. In general, the more substituted the carbocation is, the more non-hydrogen things they have that it's on it, the more stable it is. So a secondary would be somewhere in between the tertiary and the primary carbocation in terms of stability. The order of reactivity for SN1 reactions start with the benzylic or allylic carbocations being the most reactive, followed by tertiary carbocations, secondary carbocations. Primary are much less reactive in an SN1 reaction than the others, and methyl is even much less reactive than the primary. Now, in terms of the benzylic and allylic carbocations and why, or alkyl halides I should say, and why they're so reactive in an SN1 reaction, it has to do with the stability of those carbocations. What you notice is when an allylic alkyl halide like this, where the leaving group is one carbon away from a double bond, forms a carbocation, it's a very stable carbocation because I can draw a resonance structure for it. This double bond can move to over here, giving me a different carbocation. The positive charge is shared between these two carbons. Either of these carbons can react to give me two different possible alkyl bromide products, or alkyl iodide products, I should say. But the fact of the matter is the reason why these allylic alkyl halides are so reactive is that the carbocation formed is so stable.